I'm recording now, and I'm gonna go ahead and share my screen. Um, y'all can see priority queues, right?
Yeah, we can see it.
All right, thank you. Thank you as always. Okay, so today's topic is the priority queue, and some motivation behind this data structure is specifically, as we've seen so far in the course of, 221. A data structure is more or less useful depending on which operation you decide is the most important, right? So if, very, very fast insert is your top priority, you're going to pick, some certain data structure that implements that well. Or if very fast lookup is your top priority, you're going to pick some data structure that implements that well. Well, in the specific scenario in which maintaining a minimum or maximum element in your structure is of the utmost importance, then a priority queue is the ideal data structure. So whereas for vectors, we are very space efficient, we can iterate through them very quickly. Or with maps, they're not space efficient, but the lookup is very fast. One of the benefits of a priority queue is that push and pop the minimum is ideal. So that is some motivation. Don't really want to read all this text. But in this course, we kind of break up the priority queue into three different categories. So there's the unsorted priority queue. And this one is kind of cheating. I think this is kind of cheap. I wouldn't even really count this as a legit priority queue. We'll talk about this in a second. We've got a sorted priority queue, which again is a little bit of a hack. And then we've got a heap priority queue. A heap, also known as a binary heap, is going to be the majority of the focus for today. So an unsorted priority queue, a little bit, it's kind of cheap. It's not really much of a priority queue. Essentially, it is just a regular vector or a regular list, whatever it is. And whenever you push or pop, you do so in such a, well, whenever you push randomly, but whenever you pop, you do so in such a way that you return the minimum or maximum element, depending on what you're looking for. And the reason I say this is kind of cheap is because you just got this random unsorted vector and you just define the pop operation to just always give you the minimum. And if y'all remember from the earlier part of this course, finding a vector minimum is going to be O of n because, potentially you've got to sort and traverse through the entire length of the array. It is kind of cheap because there are more elegant ways to maintain what this minimum element is, rather than just finding it every time you need to find it. So a sorted priority queue kind of is a little bit of an upgrade. It kind of, if you see the difference between these runtimes, between these slides, you can see you're making push more expensive by sorting your queue. So it used to be O of one push because it was a random insert. Now it is a careful insert, but the reward for that is that finding the minimum or popping the minimum, maximum, whatever it is now a lot less expensive. So again, it's kind of cheap, not really your elegant priority queue, but the idea here is if it's important for you to be able to pop the minimum element, maybe you have to do this many times, then every time you insert, you make sure that you insert in order. That way, popping all of the minimum elements can be done in O of one time. And between these two different approaches, the unsorted priority queue and the sorted priority queue, what I want you to notice is that we are kind of juggling between linear and constant runtimes for our two different operations, right? As you can see, we either have linear push and constant pop, or we have constant push and linear pop, right? Well, the binary heap provides a solution that is perfectly in between the two of those. So binary heap gives you a solution where push is log n and pop is log n, which for your general case, actually building this thing is going to be significantly more efficient than it was for the sorted slash unsorted priority queue. Notice that we lost the term sorted. A heap priority queue is not technically sorted the way that like a binary search tree is sorted, or the way that like a sorted list would be sorted. And we're going to talk more about what this actually means. It kind of loosely preserves the order of the elements. So how does a binary heap work? Well, uh, as you can see in this picture, it looks like we're looking at some kind of tree structure. So you can see, right? So very similar to a binary search tree, we have nodes, and these nodes have children. Each node can have two children, and there seems to be some rules about, how parents are connected to their children, so on and so forth. So the main difference between a heap and a binary search tree is that there is no less than greater than operator being tied to left and right. So remember, for the binary search tree, you look at the parent node and you send everything less than that parent node to the left, and you send everything greater than that parent node to the right. You can see this is a pretty stark example. This would not be a valid binary search tree, right? Because we sent 3 to the left and we sent 2 to the right. So the idea behind the heap is that we're not sorting things perfectly. We're sorting them just good enough. So the only sorted order that will be maintained in a heap priority queue is a path from a node to a leaf. The path will always be sorted. So what do I mean by that? If you look at this path, like for instance, you pick any path, for instance, 0, 2, 7, this path is sorted in order, or 0, 3, 4, this path is sorted in order, or 0, 3, 10, this path is also sorted. And so maybe if your intuition is starting to, if the wheels are starting to turn, maybe you can see why this is ideal for implementing a priority queue, this type of structure, because as you can see, we've got all these sorted paths, and in order to reach the bottom or the top of the structure, it's going to take log of n time because it is a tree. So this doesn't make complete sense yet because I haven't actually done an example, but intuition, get the juices going. The point that I'm trying to make is that this is a very, very general case, like general more so than a binary search tree. And as you can see, every path is going to start with the minimum element, and that is going to make our push and pop more efficient than the other approaches. So one thing that's important with the binary heap is that we label all of these indices in the data structure according to a line, right? So we just count them. We count 0, 1, 2, 3, 4, 5, 6. And we will, I'm going to explain in more detail later why this is important. But for now, I think what you need to know the most is that we insert in order to make this tree as ideal as possible, right? So for instance, if we are inserting to this tree that we have on the right, we are going to insert at the next greatest unfilled index, which in this case is going to be 6. Imagine we put something at 6, the next insert is going to happen at 7, and then 8, and then 9, 10, so on and so forth, all the way until we fill up a level. And no matter what the element is that we insert, greater than 0, less than 0, greater than 2, less than 2, no matter what it is, we always insert at this next greater index. And then we, similar to like AVL or red black, we handle the insert case by case to put it in the right position after we've initialized it. So the algorithm that we're going to use to handle, correcting the structure once we've performed the insert is going to be called upheap. So why is it called upheap? What does this make sense as? So we insert 12. As you can see, we happen to put this node in a good spot, right? So remember the rules before was that every path from a node has to be in sorted orders. So 0, 3, 10, 0, 3, 4, 0, 2, 7, 0, 2, 12. Seems like every path is sorted. Seems like this is legit so far. Maybe as a rule of thumb, you can just think every parent must be less than its children, right? So 0 is less than 3 and 2, 3 is less than 10 and 4, 2 is less than 7 and 12. Seems legit. So we just happen to put this node in a valid spot. But what happens if we put a node in an invalid location? So inserting 1, as you can see, we're going to put it in the next available index, which is going to be 7. And this causes problems because now we've drawn a path 0, 3, 10, 1 that is not in sorted order. So we need to fix this by calling an algorithm called upheap. It's called upheap, as you can see, because we're going to be moving this node up the heap to the position where it belongs. So if we insert a node and it happens to be less than its parent, we just swap the two. Go ahead and swap the two, please. Yeah, there you go. And we call this algorithm recursively on the node until the structure is completely valid in every location. So now that we've swapped 1 and 10, this relationship is now valid, right? Because the path from 1 to 10 is in sorted order. But as you can see, we still have 3, 1, 10, and 0, 3, 1, 1, 10. These are not in sorted order, so we have to call upheap. We have to call upheap again, and looks like that. And now the structure is valid. As you can see, 0, 1, 3, 10. All of these nodes you can see when you're looking at the parent is always less than the children, seems to check out everywhere. As you can see, um, this operation is at maximum log of n time, right? Because we have a binary tree structure, something similar to a binary tree, which means that the height of the data structure is always going to be log base 2 of n, n being the number of elements. And so the longest hypothetical path that we would have to rearrange to keep that path in sorted order is log of n, right? Because base to base to root or root to leaf is at maximum log of n. So push is maximum a log of n operation because we would only have to check that many paths, that many nodes on the longest path. Okay, so now what about pop? So pop is going to make use of an algorithm called downheap, a very similar idea. So when we pop, we are always removing the minimum. Remember, a priority queue exists to pop the minimum or maximum element, right? So in this case, we've decided the whole purpose of our data structure is to quickly have our minimum element available. In later weeks, we're going to see why this is really useful. This is a building block for Dijkstra's algorithm. Just gonna show shortest path graph traversal, but don't worry about that just yet. Assume it's really important that we can quickly find the minimum element, and we can do this over and over and over again. Well, in this case, the minimum element is always going to be the one that is the root of the tree. Remember, as we said, every path has got to be written in descending order. Well, therefore, the smallest node has got to be the beginning of each path, which is this root node. So calling pop on this data structure will always be removing this root node. So we're never going to pop 1 or 2 or 3 or 4 until they occupy this root position. So what we do is we take the extreme element, which in this case is the one with the highest index, which is 5 at index 7. We put it in the place where we just popped. We return this 0 from the pop, and then we call downheap to sort it backwards. So this animation is going to show that off. So we swap the two. We're going to return 0, because we were trying to find the minimum. And now what we need to do is we need to rebalance this data structure, right? Because like I said before, every path must be written in decreasing order, and all of these are wrong, right? 5, 2, 3, that's wrong. 5, 2, 4, that's wrong. 5, 1, 7, 5, 1, 12, these are all incorrect. So at this level, right, looking at 5, 2, and 1, just looking at these 3 nodes, we need to put the smallest of those 3 on top, right? If we were to replace 5 with 1, then we would have 1, 2, and 5. And 1 is less than 2, and 1 is less than 5, and our structure would be valid at this level. We would have to, make the call recursively again. If we were to replace 5 with 2, then we would have 2 as the parent of 5, which is valid, but then 2 is the parent of 1, which is invalid. So we swap 5 with the lesser of these 2 siblings. So I think there's an animation that shows that happening. So we pick whichever of the siblings is the lower element, and we swap that with the node that we put at the root. As you can see, this just happens to put everything in sorted order. Imagine that caused another conflict down here. You would just call downheap again. And like I said before, because this is a somewhat binary structure, the longest path that you're ever going to have to correct in order to put that path in sorted order is log of n. So therefore, push is log of n, pop is log of n. I think that's pretty much what you need to know. So Technically, there's a third function called min, which is like peek kind of where you just want to look at the minimum element and return what that is without actually removing it from the structure. This, of course, will be O of 1 because you were just saying what exists at index 0. It's just one axis, it's just constant time. So that is pretty much all I have on the slides. I am going to do an example so that y'all can, actually see how this data structure works. I think one other thing that's really worth explaining is that when I said the priority queue exists to return the minimum or maximum element, I don't mean those interchangeably, right? Like I don't mean a priority queue is going to have the minimum and the maximum ready at the same time. But if you look at this data structure, you can see this one is built to consistently return you the minimum element very quickly. If we were to reverse our rules and say every path from the root to the base has got to be written in like the opposite orders, right? So if we said like the root has got to be the greatest element, and then the children have got to be less than that and less than that and less than that, then we've written a maximum priority queue. This is a minimum priority queue, and the two function almost exactly the same. It doesn't matter which one you choose, minimum or maximum. Depending on your use case, you will use one or the other. So, any questions on that so far? Okay. I know that's a lot of theory. Uh, that's a lot of theory. So I don't expect, you know, um, y'all to be able to visualize exactly what this looks like until we do an example. So, I'm going to go ahead and share my iPad screen. So someone say if this is working.
Yeah, we can see it.
Okay, thank you. Thank you, thank you. Okay, so um let me write a random list of numbers, and we're going to build a priority queue out of it. Actually, before I do that, um let me just draw this structure. So imagine we've got a priority queue. We're going to fill it in like this, right? As in, we try to keep the tree as complete as possible. We fill in level by level. It's going to look like this. So, one thing that I think the slides kind of didn't really cover in too much detail. Oh man, that's terrible, yo. I'm so sorry. Completely lost the ability to count for a second. Uh, so one of the things I think the slides didn't cover in extreme detail is what is this? Like, is this really a tree? Is this really a tree in the sense that we had a tree in PA4? Well, no, it's not actually a tree. So I'm gonna write that question. So is this a tree? The answer is not really. And so what do I mean by not really? Uh, when we actually implement this data structure in code, we're not building a tree, we are actually building an array. And let me prove that. Let me prove that. So uh we've got these indices, right? We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And because when we build this binary heap, we do so filling in level by level in such a consistent way every time, we actually don't need to account for nodes and pointers to other nodes because we can actually calculate, given the index of a node, what the index of its children are going to be, right? So let me just formalize that. So imagine we have some node, I'm going to call it n, right? We can find the parent of that node, so parent of n, and I'm going to write an equation here. We can find the parent of that node by well, first intuitively, imagine we're looking at 7, right? Is there some kind of mathematical relationship between 7 and 3? Well, in this data structure, there seems to be, right? 7 minus 1 divided by 2. So let's try that. So imagine we say the parent of n is going to be n minus 1 divided by 2. Well, in this case, the parent of 7 is going to be 7 minus 1 divided by 2, 6 divided by 2, which is 3. And that seems to check out so far. Now, what about for 8? We've got a parent of 8 being 8 minus 1 divided by 2, 7 over 2, 3.5. You can see clearly we need to change whatever this operator is, but it's in the ballpark, 3.5 is close. So let's go back and let's redefine this equation to be floor division, right? So doesn't change this first formula. 7 floor division 2 is going to be 3, and once again we found the parent. So given that we've got this equation right here, we've got this relationship that will tell us where the parent is given the node that we're looking at. Do we really need pointers? Like, do we really need a PA4 style tree structure? I don't think so. And let me extend this proof one level further. So imagine we have n, right? How do you find the children of n, right? Is it really necessary that we store pointers to the addresses of the children of n? Or maybe is there some way that we can calculate, imagine given a node 7 again, for instance, is there some way that we can calculate the index of where these children are gonna Oh man, I'm so sorry, y'all. Allergies are real. Man, okay. So, is there some way, given node 7, we can predict that its children are going to be stored at the indices 15 and 16? Well, the answer to that question is also yes. As you can see, 15 seems to be roughly double 7, and 16 also seems to be roughly double 7, which, kind of intuitively makes sense given that we've got 4 elements at this layer, got 8 elements at this layer, and then we're going to have 16 elements at this layer. So we can define a formula to get from 7 to 15. It seems like it's n times 2 plus 1. So let's say the left child of n is going to be, of course it could be null, but assuming it's not null, let's say it's 2 times n plus 1. So therefore the left child of 7 is going to be 2 times 7 plus 1, which is 15. And that seems to check out. And now let's look at the right child of 7, which we know is supposed to be 16 because I drew it here. Say that the right child is going to be right of n is equal to 2 times n plus 2, right? So let's say the right child of 7 is going to be equal to 2 times 7 plus 2, and this is going to be 16, which seems to check out. So I'm gonna box these formulas too. So now that we've got these formulas that mathematically define where not only the children are going to end up, but also where the parent is going to end up. Do we need to define this as a tree structure, right? Like, do we really need to store pointers to these locations if we can just calculate exactly where they're going to be? Well, the answer is no. I've been baiting at it for a few minutes now. The answer is no. Because we have these formulas, we can actually align all of our components in an array and then use these formulas to, air quote, traverse the tree. So what does that look like? I mean, we can arrange, let me draw this array right here. We can arrange all of our nodes in an array, right? Such that we, let's see, such that we perform these calculations on the indices of these arrays to implicitly define the structure of the tree, right? So imagine we're looking at node 1, right? So imagine we're looking at node 1. There we go. Imagine we're looking at this node. Well, we don't need to actually have pointers in this tree because we know that the left child of 1 is going to be, what did we say our formula was? It was 2 times n plus 1. So 2 times 1 is 2 plus 1. We know the left child is going to be 3. We know the right child is going to be 4, right? Or for instance, imagine we're looking at node 3. Well, we know the left child of node 3 is going to be 2 times 3 plus 1. We know that that's going to be 7, right? So rather than having a pointer to 7, we can just calculate where it is in this array. And hopefully, the picture that I'm trying to build is that if we have some array of infinite length, or just abstract, large length, we can expect that the relationships here are going to be logarithmic for forever, right? So if we've got some node over here, we know that its child is going to be, somewhere like here, and then its child is going to be some distance further, and then its child is going to be some distance further, and then its child is going to be some distance further. And as you can see, we're roughly doubling the distance between parent and child at each iteration. Therefore, to traverse a path, right, going from like parent to child is going to be log of n, right? It takes log of n to get to the end of this data structure. So this seems to fit all of the requirements that we had before for a binary heap, and we did so without using any pointers, which, I think is ideal. So just as an example, imagine we've got an array, and we're looking at this array, and for instance, we know that we're looking at, we've got some node at index 37. We want to calculate the parent. We know, well, the parent was probably somewhere over here. We know that the parent of 37 is going to be located at 37 minus 1 floor division 2, which is going to be 36 floor division 2. It's going to be 18. Boom. We know that the left child of 37 is going to be stored at 2 times 37 plus 1, which is 75, right? So voila. This is what our data structure actually looks like. So the tree is helpful for humans. So if you're trying to conceptualize what the binary heap is, I think this is a useful thought experiment. But really, a computer only needs this. It only needs the array. And hopefully that sheds some insight on why it is so important that we build the tree in the order that we do, right? We fill it in like these levels every time. And it also is maybe serves to be an explanation of why we consider this data structure to be in the same category as the so-called sorted and unsorted queue, which were just vectors themselves. Okay, so the next exercise I want to do is I want to actually build a binary heap. So imagine we take some random, or my best attempt at random list of numbers, and I'm just going to do all the digits like I normally do. So let's build a binary heap out of these digits. So what's that going to look like? Well, the binary heap, we're just going to start filling in the indexes level by level. So this is going to be the first iteration. As you can see, this is done at index 0, right? So we're all good so far. The next index that we're going to be looking at is, index 1, and then index 2, and 3, 4, 5, 6, so on and so forth. The next insert we're going to do is 9. So we're going to put it at the next available location. The next insert we're going to do is 1. I'm going to put that at the next available location. And as you can see right away, we have got an issue because right here, this is invalid. We've got a parent that is greater than its child. And this is a problem, right? Because whenever we call pop or minimum, all that's going to do is going to say return, assuming that this is stored in an array, return array 0. So back to the example before, the cool thing about storing a binary heap in an array is that the root is always just going to be the first index of this array, right? Because it's at position 0. So imagine the time comes, like after all this talk, of us talking about why it's important that we get the minimum element out of this data structure. You know, the day comes and we need the minimum element. If we leave the structure in this state, we are returning the wrong element, right? Because we want to be returning 1. So we have to call the algorithm up heap, right? We inserted 1 here, and we have to move it up the heap. So we have to actually make it change places with 7 in order for the minimum or pop operations to still be viable. As you can see, this returns everything back to normal, and now we're good again. So the next element we're going to insert is 3. And as you can see, it's got to be at index 3. So that is going to be here. Once again, we've got an issue because this path from the root 193 is no longer sorted. So we're going to call up heap starting on node 3, and we're going to swap it with its parent. So that's going to look like this. Let me put 9 down here. So 3 and 9 swap places. And then once again, every path from the root is in sorted order, and the element at array 0 is the minimum. So we seem to be all good. Let's go ahead and insert, see, 3 was the last one we did. Let's insert 5. 5, I don't think will cause a problem. We inserted 4, which is the next available position. Yeah, that seems like it's good so far. I don't see a problem with that. Let's insert 2. So we're gonna want to insert 2. Let me redraw these positions. I got a little bit off track. We're gonna want to insert 2 here. So 5 and 6. We're gonna want to insert it here. And this is going to be a problem because once again, look at this path. We got 1, 7, 2, not in sorted order anymore. So we're going to swap 2 and 7. This algorithm is called up heap because we inserted 2 here and we moved it up the heap. Yeah, the name is, I think, pretty fair. And once again, everything is sorted. See, we inserted 2. Let's insert 8. This, I don't think this gives us a problem. I think that's valid. I'm going to go ahead and draw in the next index, which is going to be 7, right? So we're going to insert the next thing here. See, we're going to insert 6, and as you can see, putting 6 here is no bueno. We're going to have to call up heap on 6 and move it up the heap. So swapping the positions of 6 and 9. We're going to insert 4, which, as you can see, will be, again, done at the next available location. So that'll be here. And we're going to have to move 4 up the heap. So we're going to swap 6 and 4. 4 and 6. Seems to be good. And then we're going to insert 0. So that'll be done at this location, which is 9. And that's going to look like this. As you can see, we have to move 0 up the heap. So we've got to switch 0 and 5. So that's going to look like this. And then here's a situation where we need to call up heap recursively again, right? So we need to call up heap on 0 and 3 and swap those two. So 0 and 3. And then one last time we have to call up heap on 0 and 1 and swap them like so. And now our data structure is completely sorted. And just as a reminder, as before, what's really going on here under the hood is that we're looking at an array, and these elements exist at the different positions in the array. So what we've got 9 elements, so 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to go ahead and write these indices in. So we got what we're really looking at, and I'll go ahead and add an extra space. What we're really looking at is this. So sorry, y'all. So now I've got 7, 8, 9. Okay. So what we're really looking at is we've got the elements in our array. So we've got 0 at index 0, we've got 1 at 1, 2 at 2, got 4 at index 3, 3 at 4, 7 at 5, 8 at 6, 9, 6, and 5. So this is our heap. It's going to look like this, actually in memory. And drawing the tree is helpful for a human, but really, computer sees something more similar to this. Okay, so now that we've done that, let's go ahead and practice removing the top element. So I'm going to just go ahead and draw this again. So if we know that our indices are going to line up perfectly or more or less perfectly, like so, 7, 8, 9. Let's go ahead and draw in our elements. So we've got 0, 1, 2, 4, 3, 7, 8, 9, 6, 5, and just draw arrows to kind of make this make more sense. Oops. Okay. And I think this is confusing the way I did this. We do should be a left arrow here. 6 and 5. Okay, so if we remove the minimum element here, we are so imagine we call pop on this priority queue. That's going to return 0. And then also we're going to have to do potentially down heap on the longest path, which in this case, or I guess in any case, the longest path is going to be a log of n. So pop is going to first return the minimum element and then call down heap until the structure is once again sorted. So let's go ahead and do that. So we first return 0 and then we move the extreme element, which in this case this is the extreme element, to the highest position. So once we return 0, our new data structure is going to look like this. So 5, 1, 2, 4, and the rest is just going to be the same. I just need to copy it. 8, 9, 6, 5. Okay, and so now we call down heap until everything is sorted. And as you can see, we've got to pick between these two, whichever one is the minimum, and then swap the minimum of those two with 5. So let's go ahead and do that. It seems like 1 is the minimum, so we need to swap positions 1 and 5. And again, this algorithm is called down heap because we're moving 5 down the heap, big whoop. And now once again, we're going to have to call down heap on 5. So we compare its children, 3 and 4, and we're going to swap the minimum of those two with 5. So we're going to swap 5 and 3. So there it is. And I forgot to remove 5 initially, but we would have removed it as soon as we put it up here at the root. So this is actually complete. So let's just practice that another time. So let's pop from the queue again. That's gonna return 1, and then now we've got to call down heap on potentially the longest path once again. So assuming we do that, we return 1. We're going to pop the extreme element and put it here at the highest position, and we're going to call down heap until everything is sorted. So we pick the minimum of these two elements, which in this case is 2, and we're going to swap that with whatever is currently at the root. So 6 and 2 need to switch places. Let's see. 2 and 6, and I think that fixes it. I think we're good. Now if we pop again, that's going to return 2. So we now put the extreme element, which in this case is now 9, here at the root, and we call down heap until it's sorted. We now have to pick between these two, which one is the minimum, and then replace that with whatever the current root is. So 3 and 9 switch places. As you can see, this is not yet finished, so we have to recursively call down heap one more time, because we have to sort out this nonsense. So we've got 4 and 5, we pick the minimum of those two, and swap the root, and that gives us 4 and 9, and everything is once again sorted. So I could keep doing this for forever. I don't really think I need to. I think this is about as much of a point as I need to prove. So maybe as just some recap. Uh let's see, this is where I define so push. I'm just gonna write some notes. So push is going to be an O of log n operation because hypothetically, if you push an element to the next available location, let's just call it X, you're going to have to make swaps on the longest path all the way up to the root, potentially to keep this thing in order. And that longest path is log of n, which is why push is log of n. And likewise for pop, uh, the pop is also going to be log of n because when you pop this element from the top and you put the extreme element here, you potentially now need to go resort on the longest path, and that longest path is log of n. So in coming weeks, we're going to talk about Dijkstra's algorithm once we get to graphs, and we're going to see why it is actually super important to have a data structure that can very quickly and efficiently maintain the minimum element in the same position every time. Uh, just to summarize what we've looked at so far today, we've seen that uh, because we define the binary heap so rigorously, we don't actually need to create a tree structure. So we don't actually need to get in the weeds with pointers and addresses to build the structure, because when we build it in such a way, we can actually calculate wherever the parent and child nodes are going to be according to these formulas, which I wrote out here. And because we have those formulas, we can represent the binary heap in an array structure that looks like this. And as you can see, if we track where the parents and the successive children are, you can see they're getting roughly about 2 times as far apart at each level, which makes sense as to why it takes log of n operations to get from the beginning of the queue to the end of the queue. Um, so knowing that traversing the beginning of the array to the end of the array is going to take log of n time, that means that pushing an element is going to take log of n time because potentially we need to rearrange the largest path, and likewise popping from the path is going to potentially take log of n time because again potentially we need to rearrange the longest path. And this is because we said earlier to be defined as a valid priority queue, every path must be written in descending order. So, or I guess in this case, ascending order. If I've mixed up those like descending and ascending, don't worry about it. Uh, this could just as easily be done. We could we could just as easily have a maximum priority queue, which looks something like this, and it's really no different at all. Uh, right? Like this is just about exactly as useful as the other one, just depending on our use. So I think that about wraps it up. Let's see. Stop moving. Okay. Does anybody have any questions? No questions? Nothing at all?
No, pretty straightforward.
Okay, cool. Yeah, I mean, I think y'all have got what PA5 to work on, so it's probably nice to have like an easy, uh, relatively fair concept this week, I think. And then it'll be off to the races once PA5 is over, and we're gonna be doing graph theory. So that'll be a treat. But yeah, I mean, hopefully that all made sense to y'all. If you don't have questions, I guess have a nice rest of your weekend. Thank y'all for being here, like always.
Yeah, appreciate it, man. You have a good one too.